Hey everyone, welcome back to another video of mine, where today I'm going to be solving Leetcode problem 69 titled the square root of x. So we're given a non-negative integer x, and we have to return the square root of x rounded down to the nearest integer. The returned integer should be non-negative as well. So we must not use any built-in exponent functions or operators. For example, in C++, we can't use power of x and 0.5 in C++, like I said, or x to the basically power of 0.5, or the double multiplication sign operator in Python. So in example 1, we have an input x to be the integer value of 4, and our output would be 2 because, of course, 4 is actually a perfect square, and the square root of 4 is 2, and so we simply return the integer value of 2, which is actually a valid answer in bounds of our x input. So in example 2, we have x equal to 8, which actually isn't a perfect square, if you guys haven't noticed that. And so we'd output 2 because the square root of 8 is approximately 2.8. And since we were actually rounded down to the nearest integer, note that we round down always, not up, 2 is going to be returned because 2.8 rounded down to the nearest integer is going to be simply 2. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you in a few seconds how I would optimally solve this problem and go about this solution. Alright, so the brute force solution here would basically just to loop through the range of 0 to x, which in this case is going to cover all the different integers in that range, and just check if anything in that range actually is squared that equals to x, and if it is, great, we found the square root of x, and we can simply return that value. But that's going to be big O of n time, which we can obviously do a lot better, especially considering, looking at the constraints, that x is going to be less than or equal to 2 to the power of 31, which is a huge number, and so we can't have big O to the power of n because that would be just too many operations, and we simply get a TLE, or time limit exceeded. And that is why we would actually use the binary search algorithm, which, if you guys don't know, actually has a runtime of big O of log n, where n in this case would simply be the value of x, and you'll see how that works in a few seconds. So in binary search, we always initialize our 2 pointers and keep updating them via a while loop that actually checks the validation of the pointers to be in bounds of our x value. And we'll do this like so. We'll say L and R. Typically, I'll call this left and right, but for the simplicity of this code, I'll simply call them L and R. And the L variable is simply going to be our left variable, or the minimized variable, and that's going to be set initialized to 0. And our R variable in this case is going to be the maximum value, like we always have in binary search, which in this case, of course, is going to be x, right? And now we actually have to have our while loop that constantly checks for every iteration, or for every single time we actually want to validate our 2 pointers that they're actually in bounds of each other. And so I'll say, while L, or our left pointer, is actually less than or equal to R, great, we have a valid window. These 2 pointers or variables are still in bounds of each other and make a form a valid window. And now we'll actually have our middle variable, like we always do in binary search, to be the sum of these 2 variables, so L plus R, and then integer division by 2. And if you guys don't know what integer division is in Python, it's basically denoted by these 2 slash brackets, or slash keywords here. Once I declare that mid variable, I simply am going to have a series of conditionals to actually check if I've found my square root that's actually valid for x in this while loop conditional. So what I'm going to say is, if mid, I could say the power of 2 is actually equal to x, but in this case, I'm not actually allowed to use any built-in exponent functions or operators, and so I'm just going to say, if mid times mid is actually equal to x, great, we've already found the square root for this specific iteration in our while loop, and we can simply return that middle value. If, of course, our middle times middle, if it's greater than x, okay, we have too large of a value that we're looking at, and of course our square root is going to be less than this value, so we want to update our right variable, or the variable in charge for the larger values in this iteration, to be mid minus 1 to explore the smaller values, or all the values in the left half of the range of 0 to x. And of course, we'll have another final else statement or conditional here that basically checks when mid times mid, or mid squared, is less than x. And if it's less than x, we'll actually increment our L variable and set it, or update it, equal to mid plus 1 to explore the right side values of in the range of 0 to x, or basically the greater values because mid squared would obviously be less than the actual square root. And of course, if we don't actually find any valid square root within this while loop, then we can simply exit it once L is not actually in bounds of R, or once it's actually not less than or equal to R anymore, and we can simply return R, because by the end of this while loop, R is simply going to have monitored and stored the largest possible non-negative integer that actually has a square that's less than X. And so, unless I made any syntax errors here, this should be completely fine, and this should be accepted. And as you can see, this is just about as efficient as you can get. Runtime complexity-wise, this is going to be big O of log n, because of course this is just standard binary search with X instead of just an array. And memory-wise, this is going to be constant time, because we're not actually using any data structures to actually store any inputs or variables from our input. And so this is going to be just about as efficient as you can get using this binary search algorithm, beating, as you can see, 82% of users runtime complexity-wise, and 65% of users memory complexity-wise, taking 16.4 megabytes of memory and 35 milliseconds to actually run. So if you guys learned something new and enjoyed this video, please consider liking this content and subscribing to my channel. It really does mean a lot. And without further ado, I will see you guys in the next video. Bye-bye.